Hello, this is Mr. Wynn, and this video is about parent functions and transformations. And this is one of the most important lessons in all of Algebra 2. It's probably in the top 2. So, parent functions are the most basic graphs of each type. They only have the variable x and some type of identifier. They have no extra addition, subtraction, multiplication, or division. So here, for concept of y equals x, the identifier is the 0th power. Now, I think the 0th power is 1, so we really just write y equals 1 for the constant parent. Right, for linear, we have y equals x with identifier first power. Now, the first power is invisible, so we just write y equals x. So y'all should know that equation. For quadratics, we have y equals x. The identifier is the squared power, x squared. For cubics, we have y equals x. The identifier is cube power, third power. For absolute value, you have y equals x, but in those absolute value signs, those bars that we've been working with. And then lastly, y equals square root of x. That's a square root parent function because it's x inside square roots. But the identifier should be very, very obvious. Either the exponent or the symbol around x. Alright, here's what they look like. For each parent function, you need to memorize their shape and their starting point. And for starting point, I'll just say it's this point right here. So here's y equals 1. It's a sideways line. It's flat. The starting point I'll say is 0, 1. The domain is all real numbers. As it goes left forever, no infinity, right forever, pause infinity, or all reals. The range, the lowest is 1, the highest is also 1. It's just 1. I'll do it like this. It's only 1. It's by itself in the set. Is it symmetric? Answer is yes. We can cut in half. Linear, y equals x is a diagonal line. The starting point is the origin, 0, 0. The domain, how far left does it go? Negative infinity. How far right does it go? Positive infinity. Range, how low does it go? Negative infinity. How high? Positive infinity. So both of those are all reals. Is it symmetric? Yes, we can fold it in half, cut in half. Quadratic, this is a U shape. It's called a parabola. But the starting point is 0, 0. Domain, how far left? It goes negative infinity. How far right? Positive infinity, or all reals. The range, how low? The lowest is 0, and it is closed. How high? Positive infinity. So we say that, or we can say y is greater than or equal to 0. Is it symmetric? Yes, we can fold it in half. Absolute value is a V shape. Its starting point is 0, 0. Domain, how far left is negative infinity. How far right? Positive infinity, or all real numbers. The range, how low is 0, closed. How high? Positive infinity. So we say that, 0 to infinity, or we can say y is greater than or equal to 0. Is it symmetric? Yes, it is. Now, we actually don't care too much about the constant, but look, the linear, the quadratic, and the absolute all have the same starting point, 0, 0. They go through the origin, and look at the domains and the ranges. The last one is the square root graph, y equals square root x. That's what it looks like. It looks like, they call it the snap function. It's like when you snap your finger, it's the motion you make. I just say it's half of a sideways U, but the starting point is right here. Also the origin. So everything starts at the origin for now. There's a few that don't. Domain, how far left does it go? It goes left. So it goes left to 0. 0 goes right to positive infinity. It does not go into the negative area. You can't square a negative number. So, or I can say x is greater than or equal to 0. Its range, its lowest is 0. Its highest is positive infinity. Or I can say y is greater than or equal to 0. Is this symmetric? No, it's not. Alright. So the reason we care about parent functions is because we can use them to quickly sketch functions according to transformations. Everything will always be based off the parent. It's just moved up, down, left, right. It could be magnified, flipped, reflected, all that stuff. So here's how functions generally look with transformations. If we don't get the identifier, we use a different function. They'll say a times. A is a multiplier. No matter what. Here's a being multiplied, multiplier, 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 multiplier. A is a multiplier for the function. Then we have the function identifier. So they say look at graph of f, whatever it is, or here's first power, second power, third power for the exponent ones. Here's the bars for absolute value. Here's the square root sign for square root. Alright, then inside the parentheses or the bars or the square root will be x minus h. So h is inside, it's something you add and subtract to x. And then outside by itself will be k. It's something you add and subtract as well. So a is the multiplier, h and k are what you add and subtract. Now what each one do is this. A is a multiplier. If it's more than 1, you vertically stretch the picture. If it's less than 1, it's vertically compress the picture. And we always look at it as a positive. If a is negative, that's different. The negative makes a reflection over the x-axis, so like flip it upside down. Also, when I say vertical stretch and vertical compress, in geometry I learned that as a dilation. All right, H is a horizontal translation. That's just horizontal movement left and right. So it makes a good picture go left to right, but be very careful because it is opposite. There's a minus sign right here. So if I say plus 5, that really means left 5. If I say minus 3, that means right 3. All right, and then K is the vertical translation. This is up or down, it's normal. So if I have a plus 10 at the very end, it means it goes up 10. If I have a minus 7 at the end, it means it goes down 7. But every single number in an equation does something to the picture. If it's not an identifier, it does something. It either moves to the left, right, up, down, makes it stretch or compress vertically, makes it reflect or not. So if you don't understand what I mean when I say vertical stretch, here's a nice picture representation. I like thinking of a rubber band. But if I had this rubber band right here, and I had to pull it from the top and bottom, I would vertically stretch it, it should look like a very skinny and tall rubber band. So that's what vertical stretch does. It shoots upwards. It gets like taller and skinnier. For the bottom one, if I vertically compress it, that's like smushing it from top and bottom, it'll flatten out, it'll get squeezed, and it gets wider. So you can also think about it as like a multiplying your height. If you times your height by 2, you get twice as high. If you multiply your height by 1/2, it gets half as high, right? Shorter. So let's graph these. If you don't know what a graph looks like, you can always find points. You plug in x's, get the y's, and just plot them. So I'll graph this like I don't know what it is, and then we'll talk about the transformations in a second. This first is y equals absolute value x. If I plug in these values, if I plug in -6 for x, that's y equals absolute value -6. Well, it comes out as positive 6, because I know what absolute value does. So here's 6. If I do the exact same thing for all the points, I should get all these. And actually, I'm going to use black. So I got 6 here, I'll get 3 here, 0 here, 3 here, 6 there. And I'm going to plot that. So let's do this 0, 0. Let's go in order. So -6, 6. 1, 2, 3, 4, 5, 6. Left 6, 1, 2, 5, 6. Here's -6, 6. Then -3, positive 3. 0, 0. Positive 3, positive 3. Positive 6. 4, 5, 6. Positive 6. Here's my graph. So notice this is a v. That is the parent function. All right, that's absolute value parent function. All right, I'm going to look at this next graph. It's very close, but it has a +3 inside. So let's see what happens. I'm going to use red. So I plug -6 in. So y equals absolute value -6 plus 3. Well, that is absolute value of -3. What comes out is positive 3. So there's that. I'm the exact same thing, but instead of -6, I'll put a -3 in there. So -3 plus 3, well, that's a 0. What comes out is 0. All right, well, if I try putting 0 inside. So 0 plus 3, that comes out, it's positive 3 inside, comes out positive 3. All right, I'll try the next one. Let's put 3 in there. 3 plus 3, that makes it 6 inside, comes out positive 6. And then the last one, plug 6 in there. After 6 plus 3, that is 9 inside, comes out positive 9. There's that graph. All right, I'm going to plot all those points. All right, erase part of my black line on accident. All right, so we have -6, 3. Left 6, 3. There you go. We have -3, 0. Right here, we have 0, positive 3. Right here, we have 3, 6, 4, 5, 6. We have 6, 9, 7, 8, 9. Here's that graph. Notice it's the exact same black graph, but what happened? Everything shifted 3 to the left. From this point to this point, we went -3, left 3. From this point to this point, we went left 3. For all of our points, we did that. So, even here, from this point to this point, we went left 3 spots. So we know this graph, the second one, is not the parent function. It's the parent. It's still absolute value, but it has this +3. That was the h. So our h is what's inside. We're doing absolute value, so right here. H is inside right here. It does opposite. So all this is +3. We actually think -3, and -3 for x is actually left 3. So it's the absolute value, but it's left 3. I have this last one. This plus 3 is outside. I'm going to tell you that's a k value. Its absolute value is a type, but it's k. K does up and down. So if I go here, here's where we're at right now. Plus 3 on the outside makes the whole graph 3 higher than the parent. So it should be absolute value, but it's up 3. But we'll see. I'll plug it in and do the same thing. If I plug -6 inside the bars plus 3, that comes out +6 plus 3, that makes 9. But if for all these, that will be 6, that will be 3, that will be 6, that will be 9. So there's all those. Let me graph it. -6, 9. -6, +9 right here. -3, 6, -3, 6, 0, 3, 3, 6, and 6, 9. So let's compare this green graph with the black graph. It's the same black graph, same slope, same width, same height. It's not stretched or anything, but it's just up 3. All right, 2 more slides. So once you know an equation shape by its type or identifier and the effects of the AHK from the original parent function, you can quickly sketch any graph in seconds without using a calculator and use that sketch to answer very important questions. So let's look at this equation right here. The type is square root. Square root means my shape will be something like this. It's like half a sideways U. Next we're going to go in order. I see this -3. That's our A. The negative makes it reflect over x-axis. That's the correct word. That just means it's upside down. This 3 is more than 1, so it's going to be vertical stretch by a factor of 3. Alright, so I finished this first number, -3. Then I see it's +5. That's inside with x. That's the h. Remember, it's opposite though, so instead of +5, it's a -5. It's going to be left 5 units. Left 5. Alright, then I go over here to k. This -8. It's outside by itself. That's up and down. Normal, it's going to be down 8. That's it. That's all I need for my picture. I can now graph it. So you're going to always start at 0, 0. Hover over 0, 0. And do the left and right, up, down first. I'm going to do these two first. So from 0, 0, I'm going to go left 5 and down 8. So somewhere down here. Let's call this -5, -8. Always label it. Then I'm going to draw my curve. So it looks like this, but what I'm going to do is I'm going to reflect it, make it go upside down. So instead of that, I'm going to start going like this. Then, instead of just keeping it that way, I'm also going to stretch it. So I reflect it, now I'm going to stretch. Stretch means make it taller. It's going to pull it. So it's really going to look like this and be pulled lower. So there you go. There's my picture. It's not a normal curve, it's just a taller, vertically stretched one. I'm done my picture. Now I can answer important questions. Let's do domain. Domain says how far left, how far right. It goes all the way to -5. Close. How far right? It goes forever. We could also say x is greater than or equal to -5. For range, I'll do the same thing. How low? It goes down forever. Infinity is always open. -infinity. How high? -8. Closed. Or I can say y is less than or equal to -8. All right. Last slide. You can also figure out how one function changes into another function by just seeing how a, h, and k change. No need to even graph here. So we're looking at f of x right here. Oops. Changing to g of x right here. All right, now we notice both of them are quadratic type. So type's the same. We'll look at the a's. Did the a change from 5 to 5? There's no change. But h, it went from +3 to -1. So how do you go from 3 to -1? You have to subtract 4. So for h, we had to subtract 4. Alright, so really it was like this. It would be x minus 4 inside. Then for k, how to go from -7 to +4, we had to add, would increase. So for k, we had to add 11. So for k is just plus 11. Well, we explain the two changes, we get the answer. So if you have -4 inside, that means right 4. Shift to right 4. And then if you have plus 11 outside, that means up 11. So the difference between those two graphs is one of them got shifted to the right 4 and up 11, and it came to the other graph. There's no other changes. So you can analyze the change or difference from A, H, and K to see how one graph transformed to another graph. That's it. Hope you enjoyed the video. Make sure you ask questions in class. See you soon. Thanks again. Bye.